Good day, everyone. You're watching Neri Chem. I've never woken up in the morning and thought to myself, what is an acidic oxide? But nevertheless, I have sometimes looked at the facade of building work and statues from old cathedrals, for example, which have very damaged and degraded, and thought to myself, I wonder how that happens. It can't just be wind erosion, surely. Well, these two things are not actually that disconnected. In fact, they are one cause of the other. So if you keep watching, you'll find out exactly how and why. All right, so to begin with, let's just define what is an acidic oxide. So acidic oxide. Now, an acidic oxide is an oxide which hydrolyzes in water to form an acidic solution, or can act as a hydroxide acceptor. So that would be the two options. So plus water hydrolyzes to give acidic solution to accepts hydroxide anions, or acts as a Lewis acid. So I will give some examples of acidic oxides. Some will be very, very familiar because we interact with them in our daily lives, and others probably not. So one example would be carbon dioxide, CO2, can accept a hydroxide anion, and this reaction would be in equilibrium with hydrogen carbonate, which has a single negative charge, and so there's two hydroxide anions. And then the hydrogen carbonate is in equilibrium with carbonate, which is CO3 2 minus, and water. Now, carbon dioxide, carbonic acid, here we've got the carbonate anion, but carbonate is of course in equilibrium with carbonic acid. Now, this one should be very close to home. If you have a bottle of Coke, you know that carbon dioxide comes out when you release the pressure inside of the bottle. That means that the carbon dioxide was initially dissolved in the solution, and when it's dissolved in the solution, the carbon dioxide turns into aqueous carbonic acid slash bicarbonate slash carbonate, which makes it acidic, which is why it damages your teeth. Another example would be chromium trioxide, and water would give you chromic acid. Notice that this is not a redox reaction. Chromium remains in the +6 oxidation state. Now, dinitrogen pentoxide will also hydrolyze to form nitric acid. But this isn't the only nitrogen oxide which can hydrolyze to form nitric acid, but there'll be more on this a little bit later when we look at nature. Finally, I'll give one more example, which would be Dimanganese heptaoxide, which can hydrolyze to form permanganic acid. Permanganic acid. Now, dimanganese heptaoxide is a brown reddish oil at room temperature, and when it reacts with sulfuric acid, turns green. You'll see an image on screen now. So again, these are just highlighting examples of oxides which, when they react with water, turn into an acidic solution. So nature does this too, and it does it by itself. Okay, so for example, lightning strikes. Lightning strikes generate the following equation, which would be, so let me give this a title: lightning strike. So lightning strikes are going to generate acidic oxides, which then form acids, which cause acid rain, which can damage the facade of a building. So air is mostly nitrogen. It's about 70%, which is molecular nitrogen, so N2. And what can happen is you can react the nitrogen with oxygen to form nitrogen dioxide. Now, nitrogen and oxygen don't normally react together, and the proof that we have of this is that air is a mixture of nitrogen and oxygen, and therefore you don't see the reaction product in the air. What you need is the huge amount of energy that's in a lightning bolt for this reaction to occur. Now, this is a two-step reaction because, of course, first you have to generate the acidic oxide, and then the acidic oxide has to oxidize itself to form the nitric acid. So that's the reaction I'm drawing now. This is the oxidation of the oxide. Oop. And we get our nitric acid, which we can very clearly associate with acid rain because it is an acid. So there you go. The next time you see a lightning bolt, instead of saying, wow, look how cool that line of light is making patterns in the sky. Well, no, you can tell your friends, actually, it's generating nitrogen oxide, and that nitrogen oxide is dissolving in the water vapor in the air to form nitric acid, which can cause damage to the buildings that we see around us. Of course, everyone will think of you as a slight nerd, but there may be someone who may take an interest to you, especially if they're of the opposite sex. And anyway, that's one way of thinking about lightning strikes. So actually, one point just to mention here quickly is that the mechanism by which acid rain damages buildings is called acid rain neutralisation, and this is where liquid aqueous solutions of acids coming from the rain will damage buildings. However, scientific research has proven that this is not necessarily the most important factor which causes damage in buildings. Actually, it's dry deposition. Dry deposition is where you have acidic gases, so like, for example, sulfur dioxide itself, and acidic solid particles, which may have sulfur dioxide adsorbed onto them, interacting directly with the surface of the sculpture or the building. And the proportion is actually really, really, really lopsided. So a very small, very tiny amount of acid rain damage is caused by acid rain neutralization, and the immense majority of the damage is caused by dry deposition. So it is true technically to say that acid rain itself damages buildings, but it is not the primary factor. It is dry deposition, which is caused by the same acid oxides, but not necessarily in aqueous phase. So I'll give another example of nature and acidic oxides. So this would be mineral smelting. So when we want to extract metals from nature, so a lot of the time metals, like pure metals, aren't going to be available in nature because mostly, I would say, oxides are more stable than pure metals, which means that, for example, zinc, you don't just find a lump of pure metal zinc in nature. Instead, you might find some zinc sulfide, and then what you might do is you might smelt it to get zinc oxide, and you'll also have sulfur dioxide. So zinc sulfide here, this is the raw ore, and the zinc oxide, of course, that's not what you're looking for. You're looking for metallic zinc. So there's another step after this one, which is extracting the metallic zinc from the zinc oxide, which I'm not drawing here because it's not relevant to the question. We're talking about acidic oxides. So which is the acidic oxide? Is it zinc oxide? Actually, we're thinking more of sulfur dioxide, because sulfur dioxide will react with water to form eventually sulfuric acid, but it will do this having reacted first to form sulfurous acid, which is not very stable, and it will then turn into sulfuric acid. So I'll very quickly draw how this happens. So this would be sulfur dioxide plus water will generate H2SO3, which is basically your sulfurous acid. Now, this then will react with oxygen to form the sulfuric acid, which we all know and love, which is this one. Now, this obviously logically will then cause acid rain if it's about this would happen in a cloud or in an individual raindrop. The sulfur dioxide gas will, through equilibrium, dissolve into the droplet of rain, and then the droplet of rain will form the acid which we have just drawn. And I'll give an example of another. Now, I'm going to give a trick example, one which doesn't actually generate an acidic oxide, but which does generate an oxide. And this will give us the opportunity to describe why some oxides are acidic and why some oxides are not acidic. So, incomplete combustion. Incomplete combustion should be generating lots of alarm bells of carbon monoxide poisoning, and unfortunately this is how some people, how some people have died in the past. If you leave a car engine on inside of an enclosed space, as you're generating carbon monoxide, if anyone then goes into that space and inhales the air, they can, die, basically. So the reaction equation would be, and this is just any generic alkane. So here is my 16 carbon monoxide molecules, and just to balance it, we've got 18 water molecules. So my oxide here is carbon monoxide. Now the question would be, is carbon monoxide an acidic acid? An acidic oxide? No, carbon monoxide is not an acidic oxide, because carbon monoxide will not dissolve in water. Will not dissolve in water to form an acidic solution. Will not form acidic solution. Now, most teachers, most people will stop right there and they'll say, okay, that's enough for today. Let's all pack up and go home, have fun. But this is Neri chemistry. Please, come on. It wouldn't be a normal episode if we didn't go into the exact reason why in strange and complicated levels of detail. Okay, so let's just quickly go through the Lewis diagram. So carbon has 4 electrons. These are valence, of course, because it's group 14, so it has 4 valence electrons. And then oxygen is group 16, so it's 6 valence electrons. So how do we organize these valence electrons to make our Lewis diagram? So one way of drawing carbon monoxide might be like this. That would be absolutely wrong. Why is it wrong? Well, very, very, very simple. I'll draw carbon's electrons with crosses and the oxygen electrons with circles. If you do a double bond, look what happens. So here's my highlighter. Oxygen, we said, has 6 electrons. 1, 2, 3, 4, 5, 6. We said carbon has only 4. That's 1, 2, 3, 4. So that's all correct. But then look at the octet rule. Is it fulfilled? We have 1, 2, 3, 4, 5, 6, 7, 8. So oxygen completes the octet. 1, 2, 3, 4, 5, 6. Not 8. So that's incorrect. What happens if you draw a triple bond? Then you solve the issue. But something weird happens when you draw a triple bond between carbon and oxygen. Watch. So we have carbon, and 2 electrons will be just on the carbon, and then shared, you're going to have XO, XO, XO. It's kind of looking like the end of a teenager's SMS message. And then on the oxygen, you see, you're only going to have 2 electrons. But you'll see here, this electron here, which I've just drawn, was drawn as if it came from the carbon, but it did not in fact come from the carbon. If you look, carbon only has 4. So the 2 remaining electrons have to come from the oxygen. These 2, these come from the oxygen. That means oxygen has given 1 more than its own capacity for valence electrons, which means that then it incurs the penalty of receiving a positive charge. I speak of penalty, but obviously I'm just joking here. So this is my Lewis diagram. Is the octet rule fulfilled? We have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is correct. But look at the oxygen. This electron here has been given up by the oxygen into the triple bond, formally speaking, and carbon has not met that electron with its own donation, so to speak. So we have an excess of donation from the oxygen, which means that the oxygen is going to receive a formal positive charge, and the carbon is going to receive, from having received an electron but not given one back, is going to receive a negative charge, formally speaking. And then think about what happens. We spoke about, for example, hydroxide accepting as one of the conditions for an oxide to be acidic. Can carbon monoxide receive a hydroxide anion? Well, when carbon dioxide receives a hydroxide anion, the carbon has a slight positive charge because oxygen is electronegative. So if I draw a hydroxide ion, it's very happy because negative really likes positive. But look at the situation above. Look at this here. The negative hydroxide ion is going to repel the negative, so to speak, carbon, which is why carbon monoxide is a neutral oxide, not an acidic oxide, like its close relative carbon dioxide. So there you go. Incomplete combustion does not form an acidic oxide. So I hope that was very useful to you, and I will see you in the next one. Goodbye.